Preservation Data Stores, or PDS, is a preservation-aware open archival storage system being developed at the IBM Haifa Research Lab. PDS is preservation-aware storage, which means that the storage component of a digital preservation system has built-in support for both bit preservation and logical preservation. The storage is aware of the OAIS-based preservation objects that it stores and is capable of offloading functionality that is traditionally performed by the application. Among these functions you can find handling metadata, calculating and validating fixity, documenting provenance events, managing the rep info of the preservation descriptive information, the PDI, and validating referential integrity. PDS supports loading and execution of storelets, which are execution modules for performing data-intensive functions, such as data transformations and fixity calculations close to the data. Offloading metadata management and data-intensive functions to storage decreases the probability of data loss by minimizing data transfers between storage and the application. It simplifies applications by decreasing the need for data management at the application level and provides improved performance and robustness. Another important feature is the physical co-location of data and metadata, which ensures that metadata is not lost if raw data survives. Related AIPs are also co-located on the same media. PDS is able to generate AIP identifiers to satisfy the cases in which AIPs are created within PDS or cases in which AIPs are ingested without an assigned AIP ID. PDS is built on layers, each based on open standards. Employing standards takes advantage of the community's work and also enables easier replacement of components. The preservation engine layer implements the PDS API, which is externalized using web services. It's based on OAIS. The mid layer is based on the Extensible Access method, the XAMPP emerging standard that provides complex objects for bundling pieces of data and metadata and is specialized for reference data. The object layer is currently based on the OSD standard. Here you can see how an AIP is represented in the preservation engine. An AIP is built from information objects. Each information object contains a single instance of data and 0 or more instances of rep info. An AIP contains the content information, which is an information object. Each section of the PDI is also an information object. For example, the provenance contains the provenance data that lists the events in the life of the data. Its rep info may describe the specific structure in which the provenance data is kept. In PDS, rep info is also an AIP, since rep info is a shared resource in the system that requires a unique ID. It has its own rep info, thus forming the rep info recursive network. The preservation process of an AIP can be divided into 3 phases: the ingest process, in which the AIP is stored, the access process, where the AIP is retrieved, and the preservation process, which takes place in between the other 2 phases. While the data is preserved, we need to maintain the ability to restore the bits and to provide bit preservation. Bit migrations transfer the bits from one media to another when the media becomes obsolete. To maintain the understandability of the data, we need to keep the data and accompanying metadata updated. For example, when a format becomes obsolete, we may want to perform a format migration. We also continue to update the PDI and rep info. For example, a change in the knowledge base of the designated community may require adding rep info. Fixity calculations need to be performed periodically, and provenance updates need to occur at each event in the life of the data, such as migration. When we conduct data transformations, the transformation module is packaged as an AIP and preserved. The transformation result is also preserved as a separate AIP, along with the original AIP, representing another version of the original. Its AIP ID will be a version of the original data AIP ID to maintain the connection between different versions of the same data. As a result, by retrieval time, the original AIP may have several versions and copies. The following was presented in the CASPAR second review and involved the registry, packaging, and PDS components. It used MST atmospheric data from the CASPAR scientific testbeds. The scenario showed how the atmospheric scientists transited data from one format to another and how this transit affected the preserved data, keeping its usability and understandability in light of this change. The following demonstration shows the PDS archival storage functionality that was used in that demo. You'll be able to see how the PDS graphic user interface is used to manually perform these functions while complying with the OAIS preservation model. To start with, here's some background on the data. Mesosphere, stratosphere, troposphere data, or MST in short, provides wind measurements measured by a specific radar placed in the UK. This data is highly complex and preserved for the atmospheric scientific community. It requires preservation for a long period of time for comparative research. It should be kept in a format that is supported by the majority of the community to enable interoperability. The British Atmospheric Data Centre recommends using a self-describing format for this complex data. Currently, two formats compete in the community: NASA AIMS, which is an ASCII format, and NetCDF, which is a binary format. The current decision is to use the NetCDF format. In the following demo, you'll see how this data is ingested and preserved in PDS, and how PDS supports its continuous understandability and usability. Let's see how this AIP works. The MST AIP is packaged in XFDU packaging format. It contains a manifest file that organizes the package and contains some embedded metadata. The raw data and some of the metadata are provided in files external to the manifest. All these files are packaged in a single zip file. If you take a look inside the data file, you can see the NetCDF self-describing header and the binary data. To preserve this AIP, we ingest it to PDS. Inside PDS, on Ingest, the Ingest web service is called with the packaged AIP. The preservation engine unpacks the AIP, generates an AIP ID for it, computes fixity, and adds an ingest provenance event. It then creates ZAM objects and maps the AIP into them. These ZAM objects are then mapped to OSD objects and stored at the OSD. On the way back, the AIP ID is returned to the caller. Next, you'll see how the PDS graphic user interface is used to ingest the MST AIP. And here's the PDS graphic user interface that we use to trigger the PDS functions published as web services by the PDS server. We choose the Ingest AIP method, browse for the MST AIP, and send the request to the PDS server. The return value is the AIP ID assigned by PDS. After ingest, the different sections of the AIP can be accessed separately. For example, the content data repinfo. We choose the access repinfo method, insert the AIP ID we received on ingest, and send the request. The return table includes the repinfo records of the MST NetCDF AIP. The first repinfo record refers to repinfo that was stored in the CASPAR registry, and the CPID is provided. The other repinfo records refer to repinfos that were embedded in the AIP, and therefore PDS ingested each of them as a separate AIP. The resulting AIP IDs were stored as repinfo records. Let's suppose some time passes. The following scenario may take place in the future. For several reasons, it is decided to perform format migration of the preserved MST data from NetCDF to NASA AIMS format. Perhaps the NetCDF format is no longer supported. The community became biased towards ASCII formats, and NASA AIMS has become the preferred data format of the atmospheric scientists community. In addition, it was decided to add a second view path to the data, providing an image view for users with limited access permissions. Inside PDS, on load transformation, an AIP that contains a transformation module is loaded into PDS. This load operation includes the registration of this transformation module in the system and a regular ingest of its AIP into the archival storage system. After the transformation module is loaded, we trigger the transformation by calling the transform AIP method. Inside PDS, on transform AIP, both the target AIP and the transformation AIP are accessed. The transformation is applied to the content data of the target AIP. To preserve the result, PDS builds a new AIP that contains the transformed data, new rep info to interpret it, which is applied by the transformation AIP, and an appropriate PDI that is generated internally by PDS. The new AIP is a version of the original AIP. Next, you'll see how the PDS interface is used to maintain the usability and understandability and to support the interoperability of the preserved data. A transformation module that converts MST NetCDF data to NASA AIMS format is loaded and executed in PDS. We choose the load transformation method. And similar to ingest, browse for the transformation AIP that should transform NetCDF to NASA AIMS. We then send the request. The return value is the AIP ID assigned by PDS. We choose the transform AIP method and supply the AIP ID of the MST NetCDF AIP and the AIP ID of the transformation AIP from NetCDF to NASA AIMS. The return value is the AIP ID assigned by PDS to the new AIP that contains the MST data in NASA AIMS format. This AIP ID is a version of the MST NetCDF AIP. They share the logical ID part and have different version IDs. While we don't show it, in the same manner we perform a second transformation from NetCDF to PNG plot, which results in another version of the original AIP. Suppose more time passes. Now the atmospheric scientists of the future wish to access the data that we preserved. Inside PDS, on Access, the preservation engine looks up the XAM ID that corresponds with the received AIP ID and reads the appropriate XAM objects. XAM retrieves its objects from the object layer. When the AIP is in the preservation engine, it validates the AIP ID and its fixity and adds a provenance event to document this access operation. This brings us to the last phase of this demo, which shows how PDS preserves the MST data. First, we query PDS for all the versions of the original AIP we ingested. We choose the Query AIP ID set method and supply that original AIP ID. The result is 3 versions for that AIP. One is the original in NetCDF format, one is a transformation result in NASA AIMS format, and the last is a transformation result in PNG format. Now we access each of these AIPs. PDS gives us separate access to the different AIP sections. First, we access the content data of the NASA AIMS format AIP. we choose the Access Content Data as Link method that places the content data in a staging area for downloading. We supply the AIP ID and send the request. The return value is a reference to a staging area for downloading the content data. You can see the MST data in NASA Ames ASCII format. Since PDS created a complete AIP for this data transformation result, we can also access the PDI metadata sections. For instance, we can access the provenance. We choose the Access Provenance method and supply the AIP ID. The result is a table that contains the provenance records of this AIP. The first record describes the creation of the AIP, which was the result of data transformation. The others document the ingest and access operations. We can also access the fixity. We choose the Access Fixity method and supply the AIP ID. The result is the fixity record generated by PDS, which documents the fixity calculation that took place when this AIP was ingested. Finally, we access the content data of the PNG plot AIP. Again, we choose the Access Content Data as Link method and supply the AIP ID. Now you can see the MST data as a plot in PNG format. This provides us with the requested additional view path. In this demonstration, you saw how PDS can be used to ingest an AIP and access its different sections. PDS supports the continuous usability and understandability of the ingested data by enabling us to load and execute transformation modules and by maintaining the metadata sections of the AIP. Thank you for taking the time to learn more about preservation data stores.